Um, so okay, so let's get started, everyone. So I was informed by email that there was a COVID exposure in this class on Tuesday. So the protocol I was directed to follow was to wear a mask. So FYI. Okay, the plan for today again is to keep talking about these core tools for dimensionality reduction, and this is going to be basically using and interpreting the output of the singular value decomposition, which we talked about mostly on Tuesday. There's a lot of ways to think about this. We will continue with this today. I will kind of review some of the stuff we talked about on Tuesday, and then especially the rank K approximation, how to think about this to get a low rank approximation of some matrix. We'll also talk about the relation to the eigen-decomposition, which is something that's probably slightly more likely to have heard of in your linear algebra course. And so you'll see that these are tightly coupled. I like to think of the singular value decomposition as a slightly more general use for data analysis version of the eigen-decomposition. We'll see how these are related. Basically, computing one is roughly the same kind of elements as computing the other one, once you translate things in the right way. And then we will talk about the power method. The power method is one way how to compute these things, and this will give us some insight into how these things actually work. Okay, again, you'll see the power method itself is a fairly kind of simple iterative algorithm how to do this, and you can be used it's the core part, and it's kind of to get the singular value decomposition and the dimensionality reduction result. You kind of need to put some layers around stuff and kind of talk about it. But the power method is kind of the core optimization part that you can use to compute the individual pieces and how you put them together and get back to the dimensionality reduction result. Right. Okay. So that'll be the goal for the lecture today. And then we will wrap up this section on the lecture next. Tuesday. That one we will be then actually looking at some more. The goal is looking at some more kind of general problems where we would say, let's go back to the original formulation of the dimensionality reduction without having to go through the origin. How do we solve that? Called principal component analysis, and it's very similar to this. It's just a simple added step, and then we'll also hopefully look at another technique called multidimensional scaling. Multidimensional scaling is kind of can be thought of a version of dimensionality reduction, but where the inputs are different. You're given distances instead of just a high dimensional point set. And again, what powers it is going to be the results of the singular value decomposition. So again, a common theme is that the singular value decomposition of a data set, used in the right way, can give you is like a core element of lots and lots of different algorithms. And we'll see kind of a couple of them. The textbook has some other ones which we aren't going to go over in this class, and it just shows up all over the place. So it's really important to really understand how to interpret it, and which is what we're focusing on here. All right, and if you haven't looked at homework 4 yet, please so start taking a look at that. Again, the first question will be probably the most challenging thing you do. You have to put together a bunch of pieces. I know some people start looking at it already, which is great. We're getting some good questions on that. All right, and if you're just joining late again, I was told there was an exposure in here on Tuesday, so that's why I'm wearing the mask today. All right, it's a big classroom, so I assume not everyone was exposed and everything, but you know, that's and like how these things work, I don't know who the person was or where they were sitting, anything like that. All right, okay, so again, let's go back, and we're gonna start this lecture again thinking about the input to our problem is going to be A, which is going to be a matrix n by d. Okay, and I want to start by thinking about a low rank approximation of this. Okay, so the goal I want to think of, so today, the goal is going to be some A prime, which is also going to be an element of n by d, but I'm going to have that the rank of A prime is going to be equal to k. And this is interesting when k is less than is d, and we'll think of in the case when d is less than n. Okay. All right, and we're going to use towards this, we're going to use this kind of magical function, the SVD of A, right? And we're going to see a little bit today how you could go about computing this. But the output of this is going to be 3 matrices, U, S, and say V transpose, right? And it's going to have the property that you can write A as U times S times V transpose, right? So again, with matrices, I put them next to each other. That means I'm multiplying them, right? So I multiply them in this US sub V transpose, and that recovers A. So it's a decomposition of A into the product of 3 of these matrices. And these 3 matrices capture a lot of information here. We'll think of A looking like this rectangle, and we're going to get, so U is going to be orthogonal, right? So it's going to be an orthogonal kind of orthogonal matrix here. That means that these columns are going to be interesting. These are going to be the left, so singular vectors. Okay, and then there's a matrix S. This is S. What's interesting about S is only the diagonal. Everything else is going to be 0. So this part here is all zeros. Okay, and only the stuff on the diagonal is non-zero. And finally, we're going to get a matrix V transpose, right? And this is also going to be orthogonal, or V is going to be orthogonal. And that means that the rows of V are going to be interesting. These rows are going to be the right singular vectors, right? So, and then these, the elements of the diagonal are going to be interesting. Those are the singular values, right? Okay, so I've decomposed it into 3 larger matrices, but these matrices have a lot of structure. And in particular, I'm going to have that the S11 is the first singular value. This is greater or equal than sigma 2, greater or equal than up to sigma r, which is greater or equal than 0. These are all if the matrix is A is of rank R, then these are in sort of order up to the rth one. After that, they're all zeros. Okay, these are the correspond with the singular values in S. And so those are in decreasing order, and that tells me how important each kind of these stone components are. So I can, and so what we'd like to do is recover A prime. Now let's go back to this goal. We'd like to recover or find A prime, which is rank K, and we would like to find the we'll call this AK. A sub K is going to be the arg min of rank K A prime under where we do A minus A prime. Okay, so we want A and A prime to be as close together as possible. And I can use either the Frobenius or the spectral norm here. There's two matrix norms we talked about earlier. Remember, the Frobenius norm is summing up all of the entries squared of the matrix. So I take A minus A prime, I get a residual matrix, and I'd like all this, the sum of the squares of all those entries to be as small as possible. The spectral norm is kind of like I take I multiply it by a unit vector, and I'd like that to be as small as possible under all of the choices of unit vectors. We'll see how to interpret these a bit more in the context of the SVD. Okay, but I'd like to minimize this AK, this AK under all rank K matrices. Okay, so I say I might have rank R. R might be as big as D. I'd like a smaller rank. Smaller rank is kind of like reducing the dimension, because that enforces all the data must be on a k-dimensional subspace. That's what the rank is. That's what the rank is explaining. At least that's going through the origin. Okay, and there's a number of ways that we can reconstruct A sub k using the SVD. Okay, so if this guy, let's see, we'll call this VJ, and this is UJ, the jth left singular vector, VJ is the jth right singular vector, and sigma j is the jth singular value. Okay, then I can recover A sub k, it turns out, as the sum of j equals 1 up to k of sigma j uj VJ transpose. Okay, so this is one way I talked about earlier. If you look at kind of this product here, right? UJ is an n by 1 dimensional vector, right? And VJ transpose is a 1 by d dimensional vector. So the output of here, this is an outer product. This is n by d, right? So this is in the right dimensions I want for AK, which is good. And its rank is 1. The product of vector is a rank 1 object. If I multiply a bunch of kind of objects, then their rank is the minimum of all, is at most the minimum of all the ranks of those objects, right? So since each is rank 1, the output is rank 1. And I'm scaling it. I'm saying how important is it by using the singular value. These are unit vectors, so they don't contain any scale information. All the scale information is in sigma j. And if I add up k of these, the rank is at most k. Okay, what this has done is I'm choosing the most important ones, the ones with the largest sigma j. Those are going to be kind of have the largest contribution. If I used all of them, if I summed up to D, I'm going to recover A. Right, so A, I can write as sigma j equals 1 up to D, sigma j, uj, vj transpose, right? So this is recovers A. That means, that's going to mean that A minus AK is going to be J equals K plus 1 up to D of sigma J, uj, vj transpose. Okay, so everything that's left is what A minus AK is, and this is what I want to be as small as possible. Okay, I want to give a little preview about how you typically construct or commonly construct the singular value decomposition. Is the first thing you do to construct it is you try to identify the first right and left singular vector and the first singular value. This is the first one is the one that is maximizing the variation. So I can think of so V1 equals the first right singular vector is I can say that this is arg max of V such that the V is a unit vector. This is an RD that I want to maximize A V. When I multiply A times V, the result is going to be a vector. So this norm implicitly is the 2 norm. I always use the 2 norm, but I don't say anything, and I want to maximize this. So I want to find the direction which has the most variation in A. If I multiply all the data points in A and I add up their contribution, right, remember, I could think of A as being kind of a bunch of points, right? And I want to find the direction, a unit direction, V1, that if I take the dot product, when I take the dot product of these points, I'm projecting onto this line, right? The line that's going through here, I'm projecting and I'm adding up all their sum of their squared. If I just put a squared here, then this is equivalent. This is equivalent to sum of I equals 1 to n of the dot product of AI and V squared, right? So I'm projecting onto that direction through V, and I'm taking that length of the projection, the length along V, not the residual, the length along V, and squaring that. I want to maximize that quantity. So the first right singular vector can be interpreted this way. The first left singular vector, I do this kind of in the transpose space, so then I think I have D points in n dimensions. And everything works basically the same way, but you're swapping the role of n and D. Okay, but the first right singular vector, it's enough just to think about this one here. Okay, and so once I have once I have V1, it turns out that sigma 1 is going to be exactly A times V1. The norm, this norm quantity, is exactly sigma 1. In general, this is true. So sigma j is equal to A times Vj, the kind of the norm of this quantity, which is exactly project, right, which is, so sigma squared, so a little bit easier to write this way, I equals 1 up to n of AI dot Vj squared. This is exactly sigma squared. This is, if I were to unroll this row by row of A, because the output of this is a vector, each element of that vector is one of these terms, and I'm just adding them up. All right, they're one of the squared terms, right? So I'm squaring them and adding them up, and that's the squared norm. So I'm maximizing this for V1. And then for V2, I know it has to be orthogonal to V1 by definition. It have to be, there's an orthogonal matrix. V is an orthogonal matrix. So V1 and V2 have to be orthogonal. So basically, once I find V1, then I find the next V2 is the thing that maximizes everything after I've removed V1. Okay, so after I remove V1, V2 is the thing that maximizes everything that's left, the direction of like all of the residual. By itself, V2 is not that interesting, but V1 and V2 together gives me the best two-dimensional space I could project onto. Yeah. Yeah, this is partially, but this goes into what the definition of what they actually are. All right, so yes, they're ordered in this way, but V2 is defined with respect to V1. Okay, so V2 equals the unit vector that maximizes a V2 squared. So, but importantly, subject to V2 dot V1 equals 0. Okay, so the definition of V2 depends on V1. And then recursively, the definition of Vj depends on V1 through Vj minus 1. All right, so in general, Vj, this maximizes as long as such that Vj dot Vi equals 0 for I less than j. Right? So I have to know the V1 through Vj minus 1 basically in order to construct Vj. Okay, so by themselves, they aren't really that informative, but they're informative if I look at everything up to that point. That's the best subspace I could find, minimizing kind of the variation and for the subspace of everything that's left after I factored out the best thing that came before it. Okay. All right. So okay. So this has some cool implications. Okay. So again, I have that sigma j is, or sigma I is equal to A times Vi, its norm, right? This means that this is equal to a spectral norm. Remember, this is equal to, so is the max over U is such that U is a unit vector, a U, right? So if I have a unit vector and I multiply it by A and I take the norm, then the spectral norm of A is equal to the norm of A multiplied by U, such that this is maximized. This was the definition. Maybe you saw it in linear algebra class or earlier on in the semester. So it turns out that the spectral norm is the spectral actually refers to things like singular value and eigen-decompositions, and it's equal to sigma 1. So sigma 1 gives you the spectral norm. Okay. We also have, now we can also think of A minus AK. Remember, AK is the best rank K approximation of A. So what's a simple way I can write this? What's A minus AK? Remember, this is equal to sigma J equals K plus 1 up to D of, one way of thinking about this is sigma J Uj Vj transpose. All right, it's the norm of this, right? So what's a simple way, just like I could write sigma 1 is equal to the spectral norm of A. If I look at the spectral norm of A minus AK, is there a simple way of writing this? Yep.
Is it the sum of the sigma?
No, that's going to come soon. That's the answer to a question I'm going to ask you next. But yeah.
Sigma K plus
1. Yes, that's right. This is equal to sigma K plus 1, right? Because remember how each of these are defined. Once I've factored out the first K subspaces, then VK is the one that maximizes the rest, and sigma K plus 1, or VK plus 1 is the one that maximizes what's left, and VK plus 1 is the resulting norm of it, right? So, right, this is equal to the norm of A VK plus 1, right? So that's the answer is just sigma K plus 1, right? So after I factored it out, this is what's left. And that's again, this is kind of why it's as good as possible, right? This is why A sub K is the best answer, because I factor out things in a greedy fashion one by one that maximize what I can find in each of the subspaces so far. And because they're orthogonal and the Pythagorean theorem, they don't interfere with each other. I can write things kind of the norm is the sum of the squared components, basically. Okay, great. So now kind of the other norm, AF, let's look at the squared version. This is also going to have a simple way of writing this down. This is going to be equal to J equals 1 up to D of sigma J squared. The Frobenius norm, this is equal to sigma I equals 1 to N, sigma J equals 1 to D, IJ squared, right? This is the definition of the, so by definition, right, that's what this quantity is, okay? And what I've done, if I've kind of looked at row by row, and for each row, I can also write this as J equals, let's say, I equals 1 up to N of AI squared. I can take the norm of each row and sum these up. This is also equivalent by so definition. And each, so when I've used all of V, all I'm doing is I'm rotating. I'm multiplying any vector, any row by V. I'm just changing its I'm just kind of changing the definition of the bases. I'm not changing its length. So I'm just doing this again in the space of this new basis, and there each of the rows is or the, let's see, well, there I think each of the columns, maybe this is a little bit more useful. aj. So this would be the jth column. I could sum up along the columns as well. Think of it this way as well. And so if I look at the effect of the jth column, but now I do this in the rotated space, that's going to be equivalent to the singular, the sum of the squared, so singular values, sigma j squared. So if I do A minus AK for Frobenius norm, what is this quantity going to be equal to? What's a simple expression for this quantity? I had the answer a minute ago.
Is it the remaining?
Yeah, it's the ones which are left, right? Up to D sigma j squared, right? So I start after I factored out, right? The ones, if I use that A minus AK is equal to minus J equals K plus 1 up to D of sigma j uj vj transpose, right? Then the norm, I can write the norm of each of these quantities, right? So if I look at this, I can factor out, let's do the squared norm, j equals k plus 1 up to d sigma j squared. I can factor this out, uj vj transpose, and it turns out the Frobenius norm of this guy is going to be equal to 1, right? So I won't go through all of it, but kind of if you work this out, this term should be equal to 1, and then you can see this. All right. All right. Okay. This gives you a little bit more insight into the best rank K approximation. You can also do this. You can also get the best rank K AK by using the SVD. I can take UK, which is the first K singular left singular vectors here, multiply this by SK, which is just the top K of the singular values, which are just going to occur along the diagonal. And then I multiply this by VK transpose. Yeah, so actually I don't need, I can get rid of most of this. So the dimensions match up, right? And then VK transpose is just going to be the top K here. I can also just multiply these structures together. So this this is UK. UK is in N by K. SK is in right, actually I don't need this either, right? This is going to be K by K, and then VK transpose is going to be in K by D. Okay. Okay, so this is the first K left singular vectors. It'll be the first K singular values. and this will be the first k right singular vectors. Okay, and I can recover these. This is another way to get the best rank k approximation. Okay. All right. How are the questions in the chat? Okay, good. Lots of questions in the chat today. Okay. Oh. Okay. Why is the sum from k to d plus 1 equals the k term? Where are the rest of the terms? Yes. So the sum, I think what they're asking about is this expression, a minus ak is equal to j equals 1 up to k plus 1 up to d sigma j uj bj transpose, right? So there are d minus k terms in here, right? And so a minus ak, if we go back to this page, I showed ak is just the sum of the first k terms, right? That is here. This is the sum of the first k terms, and a is all of the terms added up this way. I've just taken this decomposition and I've broken it down into pieces in a simple way of understanding it. And so if I just subtract this from this, well, the first k terms in the sum cancel, right? And what's left are these k terms. And it's just a nice, easy way to see what's going on. Hopefully that answers that question. Okay, I want to connect this to eigen-decomposition, and then we're gonna have a short break, and then we'll talk about the power method, how to compute these things. Okay. Okay, so if you remember, if I have a square matrix M, and we'll say this is in D by D. We'll think of this. So it's a D by D matrix, and we'll say it's positive, so semi-definite, or positive, so definite. This will make everything nice, and we'll come back to this case. Then the eigen values, lambda j, is a value m vj equals lambda j vj. Okay, where vj is a unit vector, and is known as the eigen, so the eigenvector. Okay, so I'm multiplying a matrix by this vector, and I'm basically recovering a scaled version of this vector. This is a value, it's a real value. So I'm recovering a scaled version of this vector. Then when multiplying, that's an eigenvector of the matrix. Okay, and kind of eigen-decompositions is giving me a set. Eigen-decomposition is a set of D V1 lambda 1 up to V D lambda D of these eigenvector and eigenvalue pairs. Okay, I'm going to get this set of these, and it's going to have the property that typically in a similar way, sometimes you present this in the other order, but lambda j is going to be greater or equal than lambda j plus 1. So they're again in a sorted order. And I have that vj dot vj prime is always going to be 0. So the vectors are going to be orthogonal to each other, it turns out. Okay. And And so I can stack these inside the matrix. So V is going to be V1, V2, up to VD. This is going to be a D by D matrix, and the columns are unit vectors, and they're orthogonal to each other, so this is an orthogonal matrix. And I'll say that L is going to be a diagonal matrix of lambda 1 up to lambda D. Okay, and then the eigen-decomposition, if you remember, a decomposition is you take a matrix and you write it as a product of other matrices. Well, then I can write M equals V times L times V transpose. That's the eigen-decomposition. So again, it's like the singular value decomposition, but this applies to square matrices that are so positive definite. If it's not positive definite, then I may not have as many singular values, or some of the eigenvalue might be 0, and they might actually be things which are imaginary. There's lots of messy stuff that happens that we don't want to worry about. So we wanted to assume that M is a positive definite matrix. Okay, and I can only apply this if it's square. I need V and V transpose to be on either side here. Okay, so I need that this is V and V transpose. Sometimes you write it. Remember, V transpose is equal to V inverse. If you recall, for an orthogonal matrix, V transpose, it's the way it's the same as the identity matrix, which means that V inverse is equal to V transpose. So I can take an inverse of an orthogonal matrix this way. So I want it to be square, so I want this sort of property. Okay. Okay, so how does this relate to the singular value decomposition? Well, it turns out it's going to deal with, well, this is positive definite. I want to find a way to always get a positive definite matrix. So I'm going to write down MR is equal to A transpose A. Okay, where again, A is an N by D matrix where N is greater than D. Okay, remember, this was our setup for singular value decomposition and data points in D dimensions. I do A transpose A. This is now going to be is a D by D matrix. Okay. If I start with real values in A, then I have to have that MR has to be so positive definite if A is so full rank. Okay, if A is not full rank, then M is positive semi-definite, which means some of the eigenvalues can be 0, but otherwise it's positive definite, and I can apply the eigen-decomposition of MR here. Okay. What's neat about this is now if I write that A is equal to U S V transpose, this is from the SVD of A. Okay, and now I want to write down the what I'd like to write down is what happens if I do MR times this matrix V of the right singular vectors. All right, so these are the right singular vectors here. I'm going to write this down here, but I want to expand this out based on the eigen-decomposition. Remember, this is A transpose A times V, which is equal to, if I have transpose of a decomposition, right, so this is A is U S V transpose, and this is A transpose. It turns out what you do for that is you swap the order and you take the transpose of everything. Okay, so V transpose becomes V, and S transpose, S becomes S transpose, U becomes U transpose. So I've swapped the order times V here, okay? Okay, but what's neat about this, and I've kind of, so what's neat here is, well, now if I change the order I'm doing the multiplication, some things are going to cancel. What can you see that cancels? These two cancel. This is the identity, because U is an orthogonal matrix, which means U transpose. This is U inverse U, right? Because the transpose of an orthogonal matrix is its inverse. So U transpose U is equal to identity. And I also get this here. This is also equal to the identity matrix. So what's left is going to be V times S transpose S. Okay, and we're going to write this as V times S squared. Basically, all I'm doing is where S squared equals the diagonal of sigma 1 squared, sigma 2 squared, sigma d squared. Okay. Oh, wait. Now I've got this set of vectors here on the right-hand side and on the left-hand side. And this diagonal matrix are like scalars, because each of the sigma j squared multiplies by just one vector here. Yeah.
Here, why does S transpose S not reduce to the identity matrix? Is that just, that's
Yes. So great question. So S, remember, S was the diagonal matrix. S was, good reminder, S was this matrix where this stuff is on the, so this is S, and it's this diagonal or like rectangular version of this diagonal matrix. And so I do S transpose, so I'm going to get a D by N matrix times the N by D matrix, and all the zeros are going to cancel. I'm going to get back a D by D matrix, S squared. And the entries, so S squared, then S squared is going to be a D by D matrix with only elements on the diagonal. But these elements don't cancel out. I don't have orthogonality here. So that's why it's not the identity. This one is the one that capturing scale. And now I'm capturing kind of squared scale, which makes sense because I did A transpose times A. I'm basically A multiplied by itself. I should get something squared. And I get S squared here. And so basically what I'm going to get, if I look at what, for all right singular vectors, Vj of A, I get MR Vj gets back sigma sigma j squared times Vj, which means that each of the right singular vectors is an eigenvector of MR. And the singular value is the squared singular, is the singular value squared is the eigenvalue. So vector. Okay, so the right singular vectors of A are the eigenvalues of A transpose A. And the squared singular values of A are the eigenvalues of A transpose A. Okay. And I did MR. I can say the same thing for ML equals A transpose, right? This is now in R n by n, and so ML times U times UJ is going to be sigma J squared times UJ. So if I do A transpose, this is going to now be the so the left singular vector uj of A is the eigen vector uj of A transpose. So I can do this on the left-hand side. I get the same singular values, right? Or the same eigenvalues are still the squared singular values here. Okay, so the eigen-decomposition and the singular value decomposition are roughly the same thing. The singular value decomposition basically always works. You have data, you have messy data, it's got noise in it. You can always do this. For an eigen-decomposition, it really works when you have a positive definite matrix. That's when it kind of makes sense. You could, I mean, sometimes you can argue that these imaginary things make sense too. They're imaginary. So, if you think in a complex space, they can make sense with your imaginary friends. But in day analysis, we have real values. So we'll think of our real friends in this case, and we can always get them by taking our data matrix A and multiplying it by itself, and then we can do the eigen-decomposition. Okay, before we take a break, I want to do one last thing. If I have MR, which is a positive definite matrix, and in R d by d, I want to compute MR inverse. This is actually something we needed to do, A transpose A. This showed up before when we were doing alpha star inverse A transpose Y, right? This was kind of inside of, in linear regression, we need to take the inverse. I never told you how to take an inverse of a matrix before. It turns out it has this form. A transpose A is this positive definite or positive semi-definite matrix. It may not be full rank, but I can use the eigen-decomposition VL V inverse, and I want to do the inverse of this. Okay, it turns out that the inverse, I can push this through here, and I get V inverse L inverse V back again. So if you push the inverse into there, this is what happens. And I know that this is V transpose L inverse V. Okay, so I'm almost there. The V's, because they're orthogonal matrices, the inverses become transposes. I have to take the inverse of L. Luckily, L equals the diagonal matrix of lambda 1 up to lambda d, and that means L inverse is going to be the diagonal matrix of L1, 1 over L1 up to 1 over lambda d. So to take the inverse of a diagonal matrix, I just invert the elements along the diagonal. That turns out the right thing to do. Inversion is like doing division, and this is the right thing. And so I can take the inverse of this diagonal matrix, and so MR inverse is equal to kind of V transpose the diagonal of 1 over lambda 1, 1 over lambda d times V, right? So if you can do the eigen-decomposition, you can take the inverse of a positive semi-definite square matrix. If something is 0, I leave it as 0. That's the only other trick. That's the so pseudo inverse, if it's not, if it's full rank, I can take the inverse. If it's not full rank, these would be 0, I divide by 0. Right, the pseudo inverse is some operation you sometimes use as more stable. If it's close enough to 0, you leave it as a 0. Okay, and that kind of works in regression. Okay, so let's take a small break, and then I'm going to talk about the power method afterwards. Oh, yeah. Yeah, so we're gonna, so on homework 4, you may remember a little bit from last year, but instead of a 2-dimensional gradient descent, you're solving for the alpha parameters. There are 4 of them now, so you need to make a 4-dimensional. You'll need to make a 4-dimensional function. So the first question is, part A is setting up that function. The part B is writing the gradient of that function. You also evaluate it at a couple of values alpha, just to kind of check it out. But the x's are given to you, and the function is the sum of the squared errors function. So you need to write that down and simplify it. And then part C, that will go into your code. So then you need to write code that does it. The simplified form will be much easier to use. So I suggest kind of trying to write out that simplified form. Yeah. Oh, it's. All right, so let's get back to the lecture. The last thing I want to cover today, and if hopefully we'll get to a cool demo and Python as well, is how to compute the power method, or what is the power method, And this will be in this section, kind of each section in the second half of the class will be kind of, okay, here's a core problem, here's an algorithm, how to solve it, and then here's kind of how to interpret it or extend it. And this is the algorithm part. We use the SVD, and that was kind of how we kind of got the answer. But I didn't tell you how to compute the SVD. And I'm going to kind of tell you how to compute the, I'll start by telling you how to compute the top eigenvector. And then I'll extend this to say, okay, how do I do this to compute the top right singular vector? And from there, you can recover the rest and then iterate. Okay, so the power method is going to take as input a matrix M, which is going to be an R d by d, so a square matrix. Remember, we're doing the eigenvector. This might be A transpose A, okay, if we're doing the singular vector, and a number of iterations. I'm going to call this Q. Let's say, think about Q is equal to like 10. 10 to 20 is probably pretty good. Okay. Okay, and the output is going to be something that is going to approximate the top eigenvector. Okay. Okay, so I'm going to step 0, and this is actually pretty important. I'm going to make an initial guess. I'll index this. This is the 0 element. So this is U index 0. Okay, this is going to be in RD. It's going to have such that we want this to, well, actually we can think of this as being, yeah, so we want this to be a unit vector, and we want this to be at random. Okay, so we want to generate a random unit vector. Okay, how would you generate a random like a random unit vector?
Probably just pick two, like random real numbers.
Yeah, you could pick D random real values and then normalize it. Good, but how do you pick them? It turns out that if you just pick them so uniformly, right? I want to think of some unit vectors, which are the points on the blue line, right? The unit vectors are all the disks. If I pick them some unit vectors, right, according to the green box, I'll pick a random point here. I pick the X value and the Y value, and then I normalize this. Well, I'm more likely to get stuff in the corners, towards the corners. I'm going to get a denser distribution along here and a sparser one along the axes. And in high dimensions, this gets much, much, much worse. If you go up to like 12 dimensions, something like 90% or 99% of the mass is outside of the unit ball, inside the unit cube. Some really weird stuff happens. So that doesn't work so well. It turns out you can pick some random normal values from a normal distribution, and like D those, and then I normalize those, the vector of those, and doing that works. Okay, so that's what you're supposed to do here. Okay, I won't go into the details of how you generate from random normal distribution. It turns out there's a method you can do it from unit vectors, but it's built in to a bunch of all the libraries. So
Is it like a normal distribution?
yeah, but yeah, the standard normal distribution. And I do D as long as they're the same distribution, one-dimensional normals, and I do D of them independently, and then I take that as a vector of those and I normalize it to a unit vector, then that works. Okay, but it probably would work with the from the unit vectors, but guarantees are harder to show. You'd rather do it this other way. Okay, so you need to initialize it, and by a random vector, a random guess. This is going to be my random guess of V1, right? The top eigenvector. Okay. And then I'm just going to run an iteration, a for loop. So it'll be kind of like gradient descent, another iterative algorithm, but it's not like, it's it's not a direct fit within the gradient descent framework. So I'm going to do Q steps of this for loop, and every step I'm going to do UI is going to get, I'm going to update my guess is M times UI minus 1. Okay, so I could write this without the indices. If I didn't keep track of the old guesses, I could just, you could write it for I equals 1 to Q of U get MU. Right, I could just write it like that without the, okay, well, without the indices, but I think can be a little bit more explicit using those. And then, okay, the only problem with this is that it's not going to guarantee to be a unit vector. So I return U of Q divided by the norm of U of Q. And this will make it a unit vector. Okay, so that's the algorithm. All right. Okay, that's okay. Yeah, so not pretty short. Yeah, because short is good. Yeah.
Does Q scale with D?
Yeah, so you just care about the top one, and what Q will scale with is with the gap between yeah, so I want to say Q larger if lambda 1 over lambda 2 is small. Okay, so if there's a big gap between the first and the second eigenvectors, then I need Q to be, I need more steps. Okay, it's kind of interesting, right? So it depends not really on D. I only care about the top one, and so it really depends on how big the difference between the two eigen values are, the top two. I want to separate lambda 1 from lambda 2 here. If they're about the same, I can get confused because there are two directions that give me almost the same amount of squared norm, right? And so if they're, and anything kind of in the orthogonal subspace will look like a similar result. If they're very different, then this will converge very quickly. And that's what it depends on. Yeah, so it's a good question. Yeah. Okay, yeah, so that's the whole algorithm. You just multiply your guess by M, and then you update the guess. So what tends to happen, right? I guess I'm not going to have time to go through the full proof here, but M, if you remember, I can write M as the sum of J equals 1 to D of lambda J uj transpose. Kind of the similar trick with this singular value decomposition. This is just with the eigen-decomposition. Okay, and so when I multiply M times, or this was V, these are V. Okay. Okay, so when I multiply M by U, basically each of these gives me a different component, a different orthogonal piece of the puzzle. Okay. If you ignore, I could think of, like, let's say M prime. It's a little easier to think of this as L times V transpose, right? And so then this is basically So then if I multiply this by a vector u, I'm going to get that m prime u is going to be the sum j equals 1 up to d of lambda j, vj, and the dot product between vj and u. Right, each vj is a vector in Rd. This is not, yeah, right, this is right. And the output is a vector in Rd here, right? And so I'm saying the component along direction vj, and then, you know, there's the orthogonal component that I'm adding up and then scaled by, so lambda j. Right, and so what's going to happen is that the components along the directions with the larger lambda j are going to get stretched out more. And as I keep doing this over and over again, they're going to get stretched out more and more. Okay, so I could think of the algorithm as being m times m times m times mu. Right, so I could think of this as the algorithm, but I could write it, so this is v equals this, but I could similarly write it as m q times u, right? So instead of doing u times m times m times m times m, I can multiply all the m's together and then get u. Okay, what's going to be neat about mq is this is going to be, let's just look at m squared. M squared is going to be v l v transpose v l v transpose. And again, these are going to cancel. So this is going to be v l squared v transpose. So that means mq is going to be v l to the power q v transpose. Okay, and so the eigen values of mq are going to be lambda 1 to the power q, lambda 2 to the power q, and lambda d to the power q. Okay? So I could think of multiplying u times this vector, and it's going to stretch things out according to the eigenvalues. The larger the eigenvalue, the more it gets stretched.
Right there.
Yeah, the u is there. So this is, oh, yeah, not supposed to be there. Great, thank you. Good. You're good at finding all my mistakes. Very helpful. Okay, good. So when I multiply by u, I stretch out along these eigenvalues, and when I take them to the power q, what's going to happen? The bigger is going to get even biggest, even bigger, right? So if it starts out as 10, and if, right, so if lambda 1 equals 10 and lambda 2 equals 2, then lambda 1 cubed, right? This is going to be 1,000, and lambda 2 cubed is going to be 8. Okay, the ratio between 10 and 2 is 5. Between 1,000 and 8 is like over 100, right? So it's the ratio between them, they gets more and more stretched out, and so what's going to happen is the original vector u is going to point more and more in the direction of the largest eigenvector. It's going to be super stretched out, but then I normalize it. Okay, so there's a kind of a more mathematical proof of this and shows the rate of convergence and stuff, but I think this gives a pretty good idea in 5 minutes. So how about I show you a demo of this just to wrap this up. Okay, this was put together by a former TA in this class. We're gonna implement the power method here using NumPy. Again, I'm going to take in a matrix B. B is now my matrix M. And then, before I do this, I want to say one more thing. The power method for A, I can instead write U is a random, so unit vector. And then step one is that I'm going to, again, a for loop, I equals 1 to Q. And now I do A, I'm going to do the update of U is going to be A transpose times A times U. Okay, so instead of updating by M, I multiply times A, and then I multiply by A transpose. And this will still, and then the output is that V1, the first right singular vector, is going to be U divided by the norm of U. So I can still do this just with matrix A, and this is how you can compute the first right singular vector, compute the singular value, and the left singular vector. You can do it with some unwrapping the algebra. Some of the details are in the book. Okay, let's go and show this demo. Again, the power method's right there. I'm just doing this matrix update B times U. That's inside these Q steps. Okay, and I normalize at the end. Okay, compute a random normal vector of size D, and I normalize it. That's how I initialize. Okay, this is some input. There's some random input A, and then I get B, A transpose A. And then here's some eigenvectors and values. Looks, it's as interesting as it looks. I guess the eigenvalues are 8.9, 1.3, 0.5. Those are things you can kind of think about. And so, and this is with 4 steps. The results are going to be pretty close, right? The true answer is at the very top there, 0.47, 0.84, 0.24. I ran it 4 steps and I got pretty close to the right answer, right? The error is in the 0.04 on the first digit there. So pretty close. Not perfect. I guess the first digit, the first coordinate as well. The other coordinates are not so great. Okay, this is a really cool visualization about how this works here. And so, just show this and not. All right, it's going to be a little. So what I've done is you can imagine the data points as these blue points and the eigen or the right singular vectors scaled by the singular values as being the red and the green lines here. Okay, and then we're going to run this. And so what we're going to do is we're going to start with the random unit vector around the origin. And we've chosen a whole bunch of them that could be random, right? Just we've placed them evenly around here. We've colored them, and you'll see what happens to colors as we run this. The first iteration, when I multiply by B or A transpose A, it's stretching them all out. This was the old location, and the ones along the small singular vector, they kind of get shrunk. Those values are less than 1. The ones along the long singular vector, they get stretched out comparatively, right? And so, okay, good. I have more of the random choices starting along this direction, or it's negative. It's not unique up to the sign. If I do another step, this is now 2 steps, they're getting more and more stretched out, and they're getting more and more concentrated along this line. Even the ones that are not as far stretched out, they're pretty much pointed in the right direction, right? Only aside the ones that were very close to being aligned with the second singular vector, only those are pretty far, and those are unlikely to happen. This is after 1 more step. So this is after 4 steps. Basically, everything winds up out here. right? There are only 2 points, and they're all basically aligned with the direction that we want them to be. Okay, so that's, yeah. Okay, I'll mention one thing. You can go and play with this. If you try this on a bigger data set, it won't work. Okay, and the reason is that when you're multiplying and you're scaling and scaling, the numbers get too big. And then you get some issues with like precision instead. And you normalize at the end, but that's too late. You've lost precision because you're dealing with too big of a numbers. And so the fix is basically to, you know, what they actually do is you'll normalize at every step. So every iteration you normalize, and this will keep things from going nuts. But you can play with this demo and see what happens. So, okay, cool. We'll stop there.